Thank you. Good to be back. Today we're going to talk about applied fire modeling for power and chemical plants. This is going to be a fun one because it takes what's kind of a technical topic and shows us how to apply it out in the real world. And you clicked on it, so let's get you right into it and hit go. So the idea here is that we have situations and scenarios out in our facilities that we want to analyze and figure out what's the right approach for protection. And specifically, I'm going to talk about firewalls today and mostly transformers. But the idea is that when you have the potential for a pool fire, then you want the ability to understand how big of a fire that can be, to know, can it really damage a nearby target? So you can see in this picture, there's a firewall. And the big question is, was it necessary? Was it justified? And by the end, you'll have an answer to that. And we'll take you through the actual calculations and show you what the fire could have been. Here's an example of where some big transformers are protected with water spray systems. A lot of people have the misunderstanding that water spray is there to put a fire out when that transformer fails. That's wrong. That water spray system is there in case another transformer catches on fire and the radiant heat from the other transformer is shining or exposing this transformer. So this water spray system that you see here is to keep it cool when another one has failed. It's not to put the fire out in this one. In fact, if this one fails, there are cases where you don't want this water spray system operating, especially if it could spread the oil, make the fire worse. In this case, should there be a firewall between these two locations? There's a transformer. You can see there's containment pit. There's a nearby building, and we don't know really what that building is, service building, switchgear building. We'll answer that question. What about this? You've got two transformers, two maybe 60% capacity transformers, so you have some built-in reliability, but do you? If one of these transformers fails, is that separation distance that you have adequate? You might have built it in accordance with the code, but let's do some analysis and find out just how safe we are. We're in a this is a control room next to the turbine deck of a power plant, thermal power plant. And that's a steam turbine out there, and they are known to crash sometimes and have fires. The fires on the turbine deck aren't really that bad, but they can be pretty hot up, because they're in the upper portion of the building. So really anything in this deck is going to get roasted. Anybody in that control room, if they couldn't get out during a turbine fire, they would be killed with those windows like that. Even if it's fiberglass, you need to have some sort of rated barriers there. So we'll see how to analyze for situations like this and how to figure out what the radiant heat could be, and then is that enough to cause damage, and should we do something about it? So let's get into it. Let's take a look at computer fire models. This is where we're going to get started. The computer is our friend, and in the world of computer fire models, we were using them back when I was going to college. So hopefully you guys can take advantage of some of the improvements that have come along. We can do it on PCs. We can do it in our home. We don't have to run batches of cards through big mainframes to get answers like I had to do in the old days. So here we go. Let's talk about it. If you have to answer that question, do we need a firewall or a fire barrier? You have several questions. First is what's the importance of the target? What are we trying to protect from that transformer? What is the vulnerability of the target? Is it something that can be damaged easily? Is it something that is very sensitive? Is it a control room versus is it another transformer? What's the potential of the fire? And what we mean here is, how bad can the fire get? How much heat can this fire give off? How much damage can this fire cause? So it's an analysis of what's the potential of the fire. And then what's the cost of the wall? Because we can't just say, oh yeah, we've got a very important target that is vulnerable and the fire can cause great damage to it. It doesn't matter if the cost of the firewall is the cost of the transformer. You don't want to spend as much for protection as what you're trying to protect. So we have to keep that in mind. Next, let's talk about New Reg 1805. This is great. You know, you everybody paid for it. At least American taxpayers did. Federal government, Nuclear Regulatory Commission put it out, and it is a set of tools that we're going to get into, and you're going to be amazed at what we can do and what's available for free. The spreadsheets that are out there, and just how powerful they are, how easy they are. So let's take a look. Yes, this is just the tip of the iceberg, because you want to go in and read the entire new reg. It explains everything that's in the spreadsheet. So it details how they came up with the formulas. They're basically built from the Society of Fire Protection Engineers Handbook. They are quantitative. They will give you answers in that you want, not just good, bad, but they'll give you answers in energy and distances. Just to give you a quick rundown, the purpose of this is to give inspectors a quick way to perform easy first order calculations, and they're derived from the SFPE handbook. Okay, first order calculations. It's a gold mine. It's a gold mine. I want everybody to enjoy this because there's so much in here. The bullet points that you're looking at, there's a spreadsheet for each one of these. There's a chapter in New Reg that explains how the spreadsheets apply and how they work. So, you know, not just is there a spreadsheet to jump into and use, there's a full explanation on how to use them and, you know, how they were developed. We're going to use the one on estimating the radiant heat flux from fire to a target fuel excuse me, to solve some of those problems that we had back there. Here's some more. I'm not going to read them all to you. It's amazing how many spreadsheets are available. They're protected. They're locked. The macros won't work when you first download them. Your computer's probably not going to run the macros because it doesn't trust the source. So you're going to have to change that if you want to be able to run these run the spreadsheets. But what also you're going to see if you're in the power gen or anywhere that's got battery rooms, there's a way to calculate hydrogen generation. That's always an interesting question that we have about battery rooms. And then calculating the structural steel fire resistance. Okay, now we're going to get into the models and we're going to talk about a fire involving a transformer. And our question is, this control building, is it, you know, protected by that firewall? Did we need that firewall? Was that firewall money well spent? First, let's get into what are heat release rates so we can get a little bit further into how to model what a fire is and what's going on. So this kind of puts it into your terms, just human terms, that, you know, these are heat release rates, and it gives you an idea of how fast heat comes from an object. There's another factor that plays, you know, into this analysis. We're trying to get an idea of how big of a fire a transformer fire can be so that we have a handle on what it's going to do to our target, the control building. And this is just how we describe how big that fire is. And we talk about it in terms of watts or megawatts or kilowatts. And the range that we're looking at for when a damage can occur, you can see somewhere between that 7 megawatt and somewhere between that 30 and 40 megawatt. Those are some big fires. So we'll have to look and see how close you need to be to those big fires for them to cause damage, because that's part of the other factor, is how far close you are will determine the flux that you're receiving. And so this is interesting. In the new reg, they provide problem statements and they show you how to use the spreadsheets. And this one is for a cable tray fire. And they basically tell you that you've got a pool of fuel, that it's on fire, and it's our job to figure out the heat release rate and the flame height and figure out, will the flames touch the cable tray? So that's kind of an interesting problem. Just throwing that, showing you what it's in there. Now, our problem isn't going to be flames impinging from a transformer to that service building or that control room. Our problem is going to be radiation, right? And radiation is more of a shine. So we're going to look for how can the light of the fire shine on our object. And one of the things to pay attention to, and it's something that only the people who watch my video and read the new reg are going to know, because it's so easily misunderstood. But the separation distance that they're talking about here is from the center of the pool of the fire to the edge of the target. They do not model from the edge of the pool to the edge of the target. We have to remember that. And a lot of fire protection engineers will look at a containment and say, well, the fire will come all the way out to here, to the edge of this pool. sorry guys, the models and all of the testing has to be from a common point, and it has to be the center of the pool. So just realize that these separation distances are from the center of the pool to the edge of the target. Center of the pool, edge of the target. We got it? All right. So we're going to look at a transformer. Actually, the NRC did in their new reg, and they're going to calculate the flame radiant heat flux, in this case, to a nearby cabinet. Same kind of methodology will work for us. Now, we have to ask ourselves, how much is too much first? Because we can do all the calculations. It's pretty easy. You go to the spreadsheets, you figure out the square foot area of the pool, and you tell it basically how you tell it that distance that you want. That's it, just a square foot area of the pool and the distance, and it calculates everything else and gives you this heat release rate flux across an area. So like, how much is too much of that flux? Well, if it was on wood, somewhere in that 20 to 30 kilowatt per square meter range. You can see mineral oil, all of these are in that 20 to 30. I looked them all up independently and they all kept coming back in this range. So I did some more looking, and I looked at a variety from hardly any flux to a lot of flux. And as we started going up, you can see as we hit that 7 to 10, we start combusting material. Wood might burn and smolder, ignition of paper and plastics. Now, if we're looking at something in a control room, or vice versa, if there's another transformer there, they have control cabinets. So inside these cabinets are conduits with wiring, or just bare wiring in the cabinet. And if we have a flux that can destroy plastic, that our transformer is going to fail. We don't have to have enough flux to do some of the things on this next page. We don't have to soften or deform the metal. We don't have to destroy the structural steel. We can, simply just melt some of the plastic in the control wiring, and we'll fry a transformer. If we have the bushings that are full of paper and insulation, and they're ceramic, so they can fail very easily. So now we know how much is too much. Let's get into the spreadsheets, and let's see. Let me get you upper left. Can you tell? You probably can't. That is a cool way to do it. Let me get the mouse over and you can see. All right. The input parameters that they will be looking for, mass burning rate. See, we don't need to worry about any of that. What we're going to do is we're going to fill in the fuel area, and say, for instance, you have a 15 by 15 dike. You're going to have a 225 square foot area, and say our separation distance is 25 feet. Well, we can hit calculate, and then the next thing you know, we've picked our fuel, transformer oil, and when you hit this drop down box, you get your options of what fuel, and then from this table, it enters those constants into these formulas to first figure out what the fire is, and then to figure out, well, if the fire's not, the wind's not blowing and it's not tilted over, we're looking at it straight on. And then using these distance formulas, the heat release formula, this is all of the work that goes into the answer of 6.78. And that's how many watts we have coming in. And if we go back to the slides real quick, go to the next slide, we will see, all right, we can start to calculate these things. I'll take you back to the front end slides. There I am, back in there with you. All right, so this is another scenario, and we'll talk about it, but it's the same way we do it. We just go into the, you were on the web, now you're not, you're back into the slide presentation. But take a look at what a 30 foot by 30 foot, that's going to give us like 900 square feet. That's going to be a big fire. And with only 25 feet of separation, what's that going to do? The kilowatt per square meter is over 10. So we're definitely going to damage whatever's within 25 feet. So there are standards out there that say separation distances from transformers can be 25 feet. Some say 30 feet. Some say 50 feet. We'll look at some variety in what happens. But at 10 megawatts or 10 kilowatts per meter squared, look at what we're getting. Wood may begin to burn, smolder, lightweight materials will begin to ignite. So we're definitely burning whatever's inside the control cabinets of that transformer. All right, here's another one. We've got, this time, let's make it 50 feet. Let's call it the same transformer pit, 900 square feet, but we've doubled the separation distance. We run the calc, and now look at the answer. Now we're much more reasonable, 5.75 kilowatts per meter squared. And that gets us there in between the early signs of blistering, and it gets us much better than the 10 area. Is it perfect? No. Could we see some paint scalding? Yeah. So just be aware. Now, for our specific example that we had, back at the beginning, what we have here is a gas processing facility with a control building, 2 transformers, and a firewall. We have about 500 square feet of containment for the oil and about 25 feet of separation. If that firewall was not there, we're going to model it, okay? And we're going to say what kind of heat flux would hit that building if there was no firewall. And we get about 9 kilowatts per meter squared. So from our previous chart, we kind of know that firewall is helping, right? Anything over that 4 or 5 kilowatt per meter squared number is going to start to cause you electrical problems. So we don't want that. What about here? Should we have a firewall in between the transformer and this building? Well, what do we got? We've got, say, 15 by 15 foot pit. This is a much smaller transformer. And we're going to have about 225 square foot of oil fire. And our separation distance is 25 feet. So what are we looking at? Let's run it. 225, 25 feet of separation. Almost 7. So we've got some room for improvement here. We're kind of that borderline, right? We're like in that gray area where we're more than the 4 or 5, but we're just kind of starting to combust some materials because we haven't hit the 7 yet. But that's the kind of thing where you would look at what's inside the building. You'd make sure that you didn't have anything important on the inside of the building. You might consider putting some intumescent paint on the outside of that building. This is a decision-making tool that helps you decide whether you've got a hazard. Here we go. We put in 2 transformers to try and account for one of them failing. Now, what if the one fails and takes out the other? Could that be here? Well, we don't have them in the same pit, or the pit's far enough apart. Well, if we've got a 400 square foot pit and we go from the center to the edge, we've got about 15 feet of separation, right? Because we don't go from the edge of the pool to the edge of the pool. We go from the center of this pool to the edge of this pool. So we're really only looking at about 15 feet of separation. Plug it all in. 400 square foot with 15 feet of separation. Whoa. 13 kilowatts per meter squared. We're definitely looking at damage to the nearby transformer. Both transformers are gone if either one of these catches on fire. So that's something that, we want to use these tools for. I want to, be able to answer the questions, help y'all. If you have other scenarios that you want to run, that's what I'd like to do, is to just help. If anybody has a problem that they've got out in the field, say the insurance company has recommended that you do something and you want an answer, I'll keep everybody's names out of it, but happy to solve problems for free. And just send me an email at